بسم الله والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. سلسلة نظريات تشرح النموذج المعياري والتفاعلات المادية، الحلقة 16 وهي 16 سي، وهي تتكلم عن QED interactions عن Feynman Roles. وأيضا في هذا الفيديو أريد أن الحديث عن كتابي القادم الحلقة 54 إن شاء الله، وسنبدأ بإذن الله تعالى في الحديث عن كتاب الحلقة 54 الذي بدأت فعلا بكتابته خلال اليوم. طيب تعال نشوف هذا الأمر. طيب هذا هو كتابي، هذا هو كتابي حلقة 54 اللي هي analysis for equation for mass evolution inside the interactions cross section at LHCs، اللي هو تحدث عن معادلة شبه حدسية لتتبع تطور الكتلة داخل الانتراكشن كروس سكشن، اللي هو الكروس سكشن للتفاعلات او مساحة مقطع التفاعل بالنسبة للHCs اللي هو مصادم الهيدرونات الكبير. بدأنا بنفس المعادلة، معادلة الاف ماتريس الذي عول عليها كثيرا جدا في يعني في هذه السلسلة، عول عليها كثيرا جدا أنها تحمل تفاصيل كبيرة جدا جدا عن ما يحدث داخل التفاعل، وكما ذكرت في الفيديو السابق. بعد ذلك يعني حاولت أن أعالج الدالة الأسية كما وعدتكم. تعال نصغر طيب حاولت كده صغيرة شديد. حاولت أن أعالج الدالة اللوسية، وأيضا سويتها ب يعني كما شرحت في الفيديو السابق، عدلت الكيو 1 والكيو 2، ويعني بدل كيو عملت كيو 1 وكيو 2 وقارنتها بالاكسي 1 واكسي 2، وهي تعتبر اختلافات في معدلات تدفق المكان والزمان. بعد ذلك سويتها بالبي 1 والكي 1 والبي 1. طبعا الكي 1 والبي 1 تعتبر كمية تحرك الفوتون الداخلة والالكترون الداخل. طبعا هذه نسبة السكترينج اللي هو سكترينج interaction بالنسبة للفوتون الداخل، فوتون والكترون، بحيث انه يعطينا في الفايمن دياجرامز اللي هو فوتون الكترون داخل التفاعل، ثم فوتون الكترون خارج التفاعل. لا يوجد مادة جديدة، لا يوجد كتلة جديدة تكونت، لا يوجد شيء جديد. لكن هذا الشرح اللي هنا، الدراسة التي قمت بها هنا يمكن تعمم على كل جميع التفاعلات الدون الذرية. طيب بعد ذلك أوجدت الدلتا ام، أوجدت الدلتا ام كدالة في الدالة اللوسية، كدالة في الدي كيو على دي اكس، اللي هي الدي كيو. طبعا الكيو تعتبر ماذا؟ تعتبر مومنتوم بالنسبة للدبليو بوزون، والاكس هي قطر التفاعل. بعد ذلك سويت جبت اللوغاريتم وأوجدت مفكوك اللوغاريتم. قبل أن أوجد مفكوك اللوغاريتم طبقت في معادلتي التي جلبتها من كتاب الحلقة 48، بحيث أنه أعلى كتلة يمكن أن يتحملها الفضاء ثنائي الأبعاد هي أن الام على ار، الكتلة على ار نصف القطر يساوي هذا الرقم مضروب في 1025، وهذا ما رأيناه في الثقب الأسود. ولهذا نعتبر الجسيمات الأولية عبارة عن ثقوب سوداء هي الأخرى. طبقت هذه المعادلة طبقتها مباشرة في طبقتها مباشرة في التفاعلات الجسيمات الأولية، خصوصا في في هذا النوع من التفاعل اللي هو الكترون وفوتون، وعوضتها بدل الكتلة M عوضتها ب E على V تربيع اللي هو الطاقة على السرعة تربيع. وهنا V تربيع يمكن استخدام السرعة C سرعة الضوء تربيع. وبعد ذلك عوضته من أجل حساب الكتلة M، الفرق في الكتلة M، الفرق في الكتلة M أو دلتا M تعني الفرق بين الكميات الداخلة التفاعل والخارج من التفاعل، أو الكتل الداخلة التفاعل والخارج من التفاعل. جاءتني هذه المعادلة، ثم بعد ذلك أوجدت مفكوك الدالة اللوغاريتمية. هذا هو مفكوك الدالة اللوغاريتمية. طيب تعالوا نصغر. هذه مفكوك الدالة اللوغاريتمية. أوجدت مفكوك الدالة اللوغاريتمية، ومن هنا من مفكوك الدالة اللوغاريتمية أوجدت ماذا؟ بعد ذلك عوضت مباشرة في المعادلة التي في الأعلى هذه، وجاءتني هذه النتيجة، إنه الكتلة الخارج من التفاعل ناقص الكتلة الداخل من التفاعل تساوي 1 زائد كيو على 2 زد تربيع. زد طبعا هي هذه، زد هذه هي اللي هو الاي 3.7 في 10 أس ناقص 28 مضروبة في اي على اكس في تربيع، مضروبة اي على اكس في تربيع. انا ان شاء الله يكون الصورة واضحة. انا سأحاول أن أجعل هذا الفيديو أكبر قليلا، يعني الدقة بتاعته سأجعلها 1080. يعني أنا الدقة للفيديوهات الصعبة كلها 750 بي 720 بي. هذه المرة سأجعله 1080 حتى تكون الرؤية واضحة. طيب بعد ذلك حسبته بعدين قدمت ملاحظاتي، ويعني الملاحظات التي قدمتها هي جزء من الملاحظات، وأنا بحاول أتذكر كل مرة ملاحظة جديدة حتى أقدمها. وهنالك ملاحظة ذكرتها سأضيفها إن شاء الله، هي أنها هذه الكتلة اللي هو الفرق بين الكتل M2 ناقص M1 يجب أن تكون مضروبة في حد يعبر عن عدد الكتل، لأنه عدد الكتل ل M2 يجب أن تكون عدد الكتل أكبر من عدد الكتل ل M1، ويجب أن نضيف هذا الحد في هذا الموضوع. وبالتالي يعني هو الكتاب هذا شبه انتهى، يعني الأفكار الرئيسية فيه انتهت. ما تبقى فيه أشياء كثيرة اللي هو جزء من التنظيم، وجزء آخر من التعديل بعض المعادلات. وإن شاء الله يعني سيخرج هذا الكتاب في الأيام القادمة، يعني يا بكرة يا بعد بكرة بإذن الله تعالى. طيب هذا ما أريد أن أقوله في كتابي، والآن سنذهب إلى الفيديو اللي هو حلقة اليوم.
2 pi to the 4 delta function of the sum of the incoming momenta at the two vertices. So this means we have 4 momentum conservation at each vertex. That is enforced by the delta functions. And after we have done that, we can also easily evaluate the integral over the momentum Q. There is the Fourier integral over the momentum flowing through the propagator Q. And this is now simple because of the delta functions. So if you have this integral over Q and you see this delta function, then the integral collapses, and the result is that Q is simply replaced by whatever it is here coming from the delta function. And Q is replaced by that everywhere else in the expression. So d for Q divided by 2 pi to the 4. And also the 2 pi to the 4 cancels nicely against one of these factors from the delta function, collapses, and Q replaced by its value coming from momentum conservation. So here Q can be replaced by P2 plus K2 or by P1 plus K1, depending on which delta function you look at. After you've done the replacement, so let's say you consider this delta function, then you do the Q integration, then Q is replaced by P2 plus K2, and everywhere else you must replace Q by that sum. So that means the second delta function changes and becomes a delta function of P1 plus K1 minus P2 minus K2. That is a delta function corresponding to overall momentum conservation of the process. In either case, this remains. And remember that we already claimed that S-matrix elements will always involve exactly such a factor, and we have defined the so-called T-matrix, which is the rest, the interesting part of the S-matrix when we factor out that delta function. And now you see that explicitly from the calculation, the delta function has arisen, and therefore everything else which is not this delta function would be what we call the T-matrix element, which is the physically interesting part of the result. So Q does not only appear in the delta function, however, Q also appears elsewhere. Namely, where does it appear? It appears here in this result for the propagator. And so here in this propagator Feynman rule, Q will now be replaced by the correct value coming from momentum conservation, either this or that, which is however the same because of overall momentum conservation. So therefore we have completely evaluated everything. The last remark is this, that the factor 1 over 2 factorial will cancel when we add the contraction where x1 and x2 are interchanged. We already said that. And then we can write down the complete result of those Feynman diagrams, and this is what I will do next. So up to the factor 2 pi to the 4 times the delta function, we get the following result. This Feynman diagram, which came from the contraction from above, including the contraction where the two vertices are interchanged, because we cannot distinguish them anymore from looking at the Feynman diagram. So the result of this Feynman diagram is literally what we have now calculated except for the delta function and except for the factor 1/2. And the result is therefore the top line where the exponential functions is completely gone, all the integrals are gone, and Q is replaced by momentum conservation. So we have then U bar of P2 S2 times, let me combine it in this way, minus I E Q gamma mu times, what was it? I divided by P1 slash plus K1 slash minus M, then minus I E Q gamma nu times U of P1 S1, and then times the two epsilons, epsilon star mu K2 lambda 2 and epsilon nu K1 lambda 1. That's it. That is the exact result of this first Feynman diagram, including all the factors, and the result corresponds to I times TFI for this diagram. Okay. And if you do the same for the other Feynman diagram, then you would get the full I times TFI result. And so maybe we can just do that for completeness by applying the Feynman rules. So similarly, what would we get when we go through the identical procedure for this contraction here? When we go through the same procedure for the other contraction, then of course what happened here for the exponential functions will also happen for the other Feynman diagram. So all the integrals will cancel. We will get an overall delta function corresponding to momentum conservation, and at each vertex momentum is also conserved. And momentum conservation at each vertex means now that our Q running through the propagator from left to right is different from that Q. Here momentum conservation tells us the following. We have incoming P1 and outgoing K2 at this vertex, and Q flows from left to right, and therefore momentum conservation tells us that Q must be equal to P1 minus K2, right? That is the result for momentum conservation. And it's also the same as, you could also look at momentum conservation at the other vertex, where there is incoming K1 and outgoing P2. So then Q must be equal to P2 minus K1. So, and this is consistent because of overall momentum conservation. So, and then the result for this diagram is U bar for the outgoing electron, then the vertex minus I EQ gamma mu, then the propagator I divided by now P1 slash minus K2 slash minus M. Okay, so that is a difference. Then minus I EQ gamma nu, U for the incoming electron. And now we have to look precisely at the epsilons. So gamma mu, the index mu, is the index which sits at the vertex coupling to the outgoing electron. So that is the vertex here. This mu sits at this vertex. So which photon couples to that vertex? It is the incoming photon with momentum K1. Therefore, the incoming photon has now epsilon mu K1 lambda 1, and that mu is the same mu as this one in the first vertex. Then the second vertex is the one with the incoming electron. So that is this one, and it couples to the outgoing photon epsilon star nu K2 lambda 2. And then we have completely evaluated the two Feynman diagrams, and the second result is I times PFI for that diagram. And the full I times TFI for Compton scattering at tree level is exactly the sum of these two terms. So do you have any questions to this? Yes, please. Yes, so just to repeat this question also for the video, indeed, what I say is that these two Feynman diagrams give the complete result for Compton scattering at tree level, but this is only true if the momenta of the initial and final state are different, such that those disconnected kind of diagrams are zero. In principle, there could be such disconnected diagrams where an electron goes directly from the initial state into a final state, or the photon as well, and the two vertices do something like that, as we discussed in the exercise. So such a contraction in principle exists mathematically, but it's only non-zero if all the momenta are not changed. And that is not a physically interesting situation. So whenever the momenta are changed, then this situation is zero, and the statement that this is the full result is correct. Other questions? Mm-hmm. It has to do with it, yes. Definitely, I mean, because of translational invariance, we can integrate over the interaction Lagrangian, and the interaction Lagrangian does not depend on space, except for via the field operators. And this is the cause that the only x dependence in the end is in the exponential function. And for that reason, we obtain the delta functions from the integrals. And the delta functions are a reflection of translational invariance. Yes. So if one would modify the Lagrangian, for example, by a term like this, so L int is, for example, psi bar of x, gamma mu psi of x, a mu of x, times g of x, where g of x is some function, so-called form factor, or any function of x, then you have artificially made your interaction Lagrangian not translationally invariant. And then the interaction strength depends on x. So maybe you say that g of x is like a space-dependent coupling constant, which goes to zero at infinity, is even conceivably of interest. But then, of course, you have broken translational invariance. And in this case, the x dependence will not be just modify the Lagrangian, for example, by a term like this. So L int is, for example, psi bar of x, gamma mu psi of x, a mu of x, times g of x, where g of x is some function, so-called form factor, or any function of x, then you have artificially made your interaction Lagrangian not translationally invariant. And then the interaction strength depends on x. So maybe you say that g of x is like a space-dependent coupling constant, which goes to zero at infinity, is even conceivably of interest. But then, of course, you have broken translational invariance. And in this case, the x dependence will not be just exponential functions, and you will not get delta functions from the x integrals, but you will get terms which involve the Fourier transformation of this form factor function here. And so in our case, we have implemented explicitly translational invariance, and this is then manifest at each vertex in this construction.
طبعا الآن يعني هذا الكلام يؤكد على ما أقوله دوما على أنه داخل أو ما ذكرته أيضا في كتابي أن داخل التفاعل كله يعتمد على X مسافة، بالتالي لا يوجد لورنز انفاريانس ولا يوجد سيمتريز مكسورة، ولكن عندما تخرج يعني تعيد السيمتريز مرة أخرى، وهذا يكون على حساب الكتلة وكمية الحركة. أو كمية الحركة لها سيمتري بالمناسبة، إذن على حساب السرعة الكتلة يكون على حساب الكتلة، وهذا ما ضمنته في كتابي أنه يكون على حساب الكتلة. والكتلة لديها كما رأيت في كتابي، الكتلة لديها سقف، بالتالي عندما تصل هذا السقف فإنها تخرج من التفاعل مباشرة لتأتي كتلة أخرى تدخل في تأتي كتلة أخرى تتكون مرة ثانية حتى تصل هذا السقف وتخرج من التفاعل. إذن الكتل المتعددة التي تخرج من التفاعل نتيجة لهذه الآلية.
Yeah, it does. It breaks momentum conservation, and because it breaks translational invariance. So this form factor, if you have some physical origin, it's like an external potential which can provide energy or momentum to the system. Other questions? Hey. How many more examples of that kind should we do? The options are 0 or 1. We will continue to solve the exercise sheet where we have similar discussions, and so maybe I think we have done enough examples here in the lecture, unless you want me to do another one. It seems not so. So let us jump to the conclusion. Then the rest of the lecture would be probably about summary of Feynman rules, collect them in nice ways, and such that you can really go back to a list of rules later on. Because now our examples basically allow to read off the general case. So let us take all our examples that we have discussed and summarize the rules. I stated 1 or 2 lectures ago the Feynman rules for QED, and our examples have shown that the rules are correct, and so I will not repeat them here, but we have verified the rules by the explicit cases. But by going through the examples, we have also identified that there are actually some additional rules which I now want to summarize as well. So first of all, you have seen this factor 1 over n factorial from the exponential function, from the e to the I L int from this term usually drops out. And in our example, it drops out. Also in the example in the exercise, it also dropped out, but it does not always drop out. So sometimes it simply remains, or it remains partially because it's only partially cancelled. Sometimes they remain uncancelled symmetry factors. And this is then the term how we denote those uncancelled factors. They are called symmetry factors, and they simply arise from the fact that sometimes it happens that if you exchange x1 and x2, you do not actually get a different contraction on the operator level, but you get the identical contraction. And we have actually seen an example in the exercise, namely this one. We have seen this example in the exercise. This is a vacuum diagram. And in this vacuum diagram, all the lines from x1 and x2 are contracted. So if you now exchange the variables x1 and x2, the operator contraction is exactly the same. So it's not only mathematically equal, but it's the identical contraction. Therefore, in this case, the factor 1 over 2 factorial is not cancelled by two different contractions. And so here this diagram would involve an explicit factor 1/2, which you must not forget when calculating the Feynman diagram. And this can sometimes happen, and whether it happens or not, you have to figure out by looking at the diagram and imagining the underlying contractions. Of course, there are computer programs and algorithms to do it in general, but that is the basic principle. Similarly, it has not encountered in our example, but sometimes there are minus signs. The exercise. And the simple physical reason for those minus signs is, of course, Fermi statistics. So if you have a diagram, for example, with 2 electrons in the final state, then the state is antisymmetric under exchange of the 2 electrons, and therefore some Feynman diagrams which correspond to such an exchange of 2 electrons, they must involve a relative minus sign. And that automatically comes out from the contractions by evaluating the anti-commutators appropriately. So always the contractions are the basic tool to get a correct result, and if you translate them into Feynman diagrams, you have to watch out for those subtle details. Then there is also a rule which we found for the fermions and the lines, namely the Feynman rules for the fermions, they are spinor valued objects. So you must treat carefully the matrix structure. You have 4-component objects or 4x4 matrices, so the order of the objects matter. They are not only numbers. And the rule is that the order of the quantity is against the arrow on the fermion lines. That is the simple rule which we have seen in our examples, both now for Compton scattering and also in a previous example some lectures ago. And actually, let me also state here, this works for QED, but it's also not something that works in all cases. There are quantum field theories where the rule is too simplistic, and the simple example is if you have neutral fermions which could be equal to their own antiparticles, then the arrow on the line is not defined, and then you can write down Feynman diagrams where, for example, arrows clash and so on, and then you do not know what to do. And so what is then the correct thing to do is, of course, again, to go back to the original contractions. So always correct, go back to the original contractions. So this is always the way to obtain the correct result unambiguously with all signs and with all factors. And so that is the definition. Okay, but these are the additional rules that we have found, and there is one remaining rule, namely at higher orders. there can appear so-called loops in Feynman diagrams. For example, something like this can happen, or for Compton scattering, something like that could appear. Such Feynman diagrams, they have a higher number of vertices, and therefore they are of higher order in perturbation theory, and they involve this so-called loops. In the loops, if you ask for momentum conservation at each vertex, the momentum in the loop is not defined. And for example, here you might have a momentum Q flowing through the photon, and then you have here a momentum, for example, Q plus K, and flowing in this direction, and another momentum K flowing in the backward direction. And so for any value of K, you have momentum conservation at each vertex. Therefore, K is not defined. Q plus K is defined, but the K value itself is undefined. It can have an arbitrary value, and if you follow the derivation, then in the beginning there used to be an integral over each momentum of each propagator, right? And so here you would have initially two momentum integrals, but also integrals over all the momentum conservation at each vertex. So you get a delta function for momentum conservation at each vertex, and that will cancel some of the momentum integrals from the propagators. But in this case, the momentum integral over K remains, because K is not defined by these delta functions, and therefore, in those cases, integrals over the undefined momentum are momenta remain over undefined momenta, and they are d4k over 2 pi to the 4th power. They remain. And so from this rule, you could immediately write down the value for the Feynman diagrams, because you literally write down all the factors in the way that we know. And here, momentum conservation tells you to put some undefined momentum k here. You integrate over k, and that is exactly the correct result following from our derivation. Okay, good. That is all I wanted to say to QED. Further questions about QED? So at this point, maybe I want to refer you to the discussion that we had at the beginning of this section on Feynman diagrams. Namely, I stated that we will do it here quite briefly, because this semester is devoted to the physics of spin 1/2, spin 1, and the differences between the different spins and the different types of fields. And the derivation of Feynman rules is independent of those differences. And therefore, we are quite brief, and much more brief than we were 3 years ago. And so now you have seen the brief derivation, and I've explained you, and it's still on video, of course, all the relationships to the derivation from 3 years ago. And so I invite you to watch those videos and get all the other details of derivations of Feynman diagrams, more examples, and also subtleties in the derivations and so on. But I will not talk more about this here, maybe in the exercise if you ask me, but it's public, and therefore we can go on here. And what I want to do now is to generalize the Feynman rules for QED, namely to arbitrary quantum field theories. And then we get a set of rules how you can obtain the Feynman rules for any quantum field theory that you are given. And the field theory is defined by a Lagrangian, and then there is a recipe which you can easily understand from those examples how you get the Feynman rules for any theory. So that will then conclude our chapter on Feynman rules. So this is the summary of the general recipe. So, as in the beginning of this section or chapter of the lecture, the Lagrangian of our quantum field theory is defined to be composed out of a free Lagrangian and an interaction Lagrangian. And the free Lagrangian is exactly one of the Lagrangians that we have discussed in chapter 2 of the lecture, where we know exactly how to quantize it. So this is the combination of Lagrangians of chapter 2 of the lecture. And the interaction Lagrangian is any Lorentz invariant local combination of fields. And just to be clear, also derivatives of fields are allowed in the interactions. So, but local means that the Lagrangian contains only products of fields at the same space-time point and not at different space-time points, but derivatives are allowed. So then, how do you get the Feynman rules from here? The first thing that you can obtain is the propagators. So the internal lines in Feynman diagrams. And they come from the free part of the theory, from the free Lagrangian. They really correspond to the field quantization and the operators of the free fields with their properties that we have discussed. And so you can always obtain a very simple and beautiful recipe. Namely, you can write the free Lagrangian in this sort of schematic way, either for real or for complex fields. You can write it like this, or up to total derivatives. Okay, so what does that mean? You can always bring the Lagrangian to the form by doing partial integration such that you have a bilinear expression of fields, and between the fields you have some differential operator. And this curly D denotes a differential operator. It could be the Klein-Gordon operator, box plus m square, or it could be the Dirac derivative I d slash minus m, and so on. But you can always write the Lagrangian in this form, where this is some differential operator. So either of first or second order in derivatives. Then you can define a propagator between fields Pij, would be the vacuum expectation value of two fields, two field operators. So, in the complex case, one field has a dagger, the other field has no dagger. And in the real case, of course, the dagger is meaningless. But you can always define a propagator in this way, and it has indices, so you get basically a matrix of propagators. So what the I means is, of course, the I runs through all the fields of your theory, photon field, electron field, muon field, whatever you have. It just denotes all the fields, and so here you have a matrix of propagators from any of the fields to any other one. So all of these propagators and so-called two-point functions will of course appear in the contractions when we evaluate the Feynman diagrams in the way as we did. So and then the rule is the same as for QED, where the propagator was the inverse of the differential operator, and this is really true also in general. So we have proven that if you act with a differential operator onto the propagator, you get a delta function in position space. So if you convert to momentum space, then the momentum space propagator is just the inverse of the differential operator, where you replace derivatives by momenta. Very simple and nice rule. And so this rule is true in general. Namely, you can say it in the following way: I p tilde ij in momentum space is I times the differential operator Fourier transformed to the -1 with indices ij, where we again have the rule that I times derivatives go to momenta. So then in this way you can always obtain all propagators of any free theory. And the result is of course like this, that in simple cases if you have only a scalar, one scalar, then you might have a line like this from the Deckard scalar field to the scalar field with momentum q, and the rule is I divided by q square minus m square plus I epsilon. The I epsilon I have not explained, but let me write it down anyway. It can be derived in different ways, but if you ignore it, then you have this, and this is the inverse of the Klein-Gordon operator, where you replace the box by minus q square. Then for the Dirac spinor,
طيب معلش نرجع شوية. اللي هو البروباجيتور عن طريق الفورير ترانسفورم يعطينا يعني مقلوب الاشتقاق. نحن نعلم أن الاشتقاق يعني ماذا؟ يعني دي على دي اكس أو دي على دي تي، وهذا يعطينا معدلات تدفق الزمن. فعندما نجري الاشتقاق نجد أن معدلات تدفق الزمن موجودة في البسط، والفترة الزمنية والفترة المكانية موجودة في المقام، ومعدلات التدفق كلها يعني معدلات التدفق الفترة الزمنية والمكانية، معدلات التدفق أقصد، موجودة في البسط. طيب عندما نطبق الفورير ترانسفورم بالنسبة للمومنتوم يعطينا ماذا؟ يعطينا دي اس ناقص واحد، وبالتالي تذهب معدلات التدفق إلى المقام، لهذا طبعا معدلات التدفق تصب في مصلحة الفضاء ثنائي الأبعاد، والفترة الزمنية تصب في مصلحة الكتل والطاقة، لأنه الفترة الزمنية تعبر بتزيد بزيادة الطاقة أو الكتلة، لأنها تعبر عن التايم دايليشن والسبيس دايليشن. معدل التدفق يزيد مع الفضاء ثنائي الأبعاد لأنه يعبر عن الكونتراكشن. إذن الدي أس ناقص واحد يعطينا أن المعدلات التدفق تكون في المقام، وهذه طبعا معلومة أنا أول مرة أعرفها. معدلات التدفق تكون في المقام، وهذا يعني أنه المقام كله يعبر عن الفضاء ثنائي الأبعاد، والبسط كله يعبر عن الكتلة والطاقة. ولهذا نجد في الجرين فاكشن ونجد في البروباجيتور أن المقام يجب أن يكون أكبر من البسط. يعني هذا هو التفسير لماذا في السلاسل الفائتة دائما نقول المقام أكبر من البسط، لأن المقام يعبر عن الفضاء ثنائي الأبعاد اللي هو بموجب مقلوب الديفرنشيال اللي هو مقلوب الاشتقاق. فالمقام يكون في الفضاء ثنائي الأبعاد، كلما زاد المقام زاد سيطرة الفضاء ثنائي الأبعاد، وكلما زاد البسط زاد سيطرة الفضاء الثنائي الفضاء الرباعي أو نقول الكتلة والطاقة. الغريب أننا نجد المومنتوم ونجد الكتلة ام سمول كلها نجدها في المقام. أين هي؟ نعم هنا. الغريب أننا نجد كيو تربيع زائد ناقص ام تربيع زائد اي ابسلون كلها نجدها في المقام في مكان سيطرة الفضاء ثنائي الأبعاد. تخيل. وهذا يعطينا ماذا؟ يعطينا شيء معين لا بديل له، أن هذه الكتلة وهذه كمية تحرك هي مطرودة من التفاعل فقط، لا يوجد شيء آخر مطرود من التفاعل. يعني هذه الكتلة M small هي كتلة مطرودة من التفاعل. والكيو هي كيو مطرود من التفاعل، بالرغم انها تمثل الكيو الخاصة مثلا بالدبليو او مومنتوم للدبليو، لكن ما دام هناك مومنتوم كونسرفيشن فهذا يعطينا ان كيو يمكن التعبير عنها ب كي زائد بي، اللي هو الفوتون زائد الالكترون طالع خارج من التفاعل. لهذا كيو يمكن ان نعبر بها ايضا مطرودة من التفاعل. اي شيء موجود في المقام يعبر عن سيطرة الفضاء ثنائي الابعاد. الابسلون تحدثت عنها كثيرا في السلاسل السابقة او تحديدا في سلسلة المجال كم الفعال. الابسلون موجود في المقام وهو يعبر عن الفضاء ثنائي الابعاد غير متناظر، وهذا يعني ان الابسلون يحمل خصائص الفضاء ثنائي الابعاد، ومن ضمن الخصائص ان كلما تقرب الإبسلون من الزيرو كلما اختفت القوى الأساسية الثلاث. كلما اختفت القوى الأساسية الثلاث. تجدون هذه المعلومة في سلسلة نظرية المجال كم الفعال، وأيضا السلسلة الخاصة بنظرية الأوتار والهولوغرافي أيضا تحدثت عن هذا الأمر. وتحدثت ربما في نظرية الهولوغرافي باستفاضة عن الدولتي بين الفضاء ثنائي الأبعاد اللي هو بين ال 6 dimension أو ال 5 dimension of gravity وال 6 dimension of QED. gravity تمثل الفضاء ثنائي الأبعاد، والQED في 6 dimension تمثل فضاء مسطح اللي هو فضاء مينكوفسكي من 6 أبعاد. فهناك معلومات جميلة جدا جدا في سلسلة السترينج ثيوري. إذا نستخلص من هنا أن المقام كله عبارة عن سيطرة الفضاء ثنائي الأبعاد. وهكذا سنقرأ مخططات فايمن من هنا وللأمام، سنقرأ مخططات فايمن بهذه الآلية.
For the Dirac spinor, you have of course the following. So you have psi bar here and psi here, and an arrow from psi bar to psi, which indicates that, let's say, an electron is created here and an electron is annihilated there. Momentum flows in the direction of the electron, and the propagator is then I divided by Q/-m plus I epsilon, which is the same as I times Q/+m divided by Q square minus m square plus I epsilon. Again, the inverse of the corresponding operator. And finally, for a photon in covariant gauge with gauge fixing parameter psi equal 1, we have this propagator, just to remind you, from a nu to a mu is minus I times g mu nu divided by Q square plus I epsilon. Okay. So this is the type of rules for the different types of propagators that we have. But in general, you have many fields, many scalar fields, many spinor and vector fields, and you might even have mixed propagators from one field to another one. And the completely general rule is the one that I've listed here. Okay, so this is how you get the propagators in direct generalization. Then the next step are the vertices, and I think that probably can fit here. So for the vertices, we start with one term in the interaction Lagrangian, which would be maybe minus g times a product of some field operators, phi I, phi j, phi k. as an example. So in general, an interaction Lagrangian is a sum of many terms, and each term gives rise to one Feynman rule. So therefore, for term by term, we derive how the Feynman rules look like. And here we consider exactly one such term, which is in this case a product of three field operators times a number valued coefficient. Okay, so G should be a number, and these are scalar field or fermion or vector field operators, and I just labels generally the indices. If you have this term, then you get a Feynman rule which looks like this. Namely, we saw that from the derivation, for each interaction Lagrangian in this exponential function, you get a dot in the Feynman diagram, and at the dot you connect several lines. Namely, for each field operator, the dot connects to one particular line. So the dot connects to a line with phi I, a line with phi j, and a line with phi k in this particular case. And then in the Feynman diagram next to this, there might be propagators for those fields and so on, but the vertex connects to those three fields. And the rule is minus I times G. Where does the I come from? The I comes from e to the I times interaction Lagrangian in the exponential function for the S matrix. That explains the I. And the minus G is the prefactor in front of the field operators. So the general rule is the following. You have a connecting line for each field, and the coefficient can be written as I times and then the derivative of the interaction Lagrangian with respect to all those fields. Okay. In this way you would get here the minus G times I gives minus I times G. Okay. In this way you would get here
طيب تعالوا للجي
the minus G times I gives minus I times.
تعالوا للجي. أول شيء نحاول نصور دي هنا. تعالوا طيب جميل. تعالوا للجي اللي هو الفيرتكس. نحن ذكرنا انه المقام يعبر عن سيطرة الفضاء على بعد، ولكن في فايمان دياجرام نجد ان الفيرتكس نعبر عنها بالجي. بالمناسبة ليس الجي فقط، وإنما هنالك حد ايضا مضروبة في الجي اللي هو يسمى بالاي اي كيو. كيو هو ناقص واحد، والاي هو شحنة الالكترون، وايضا توجد في البسط. شحنة الالكترون ايضا توجد في البسط، وايضا الفيلدز كلها توجد في البسط. لكن في النهاية عندما نجري الكونتراكشنز نجد ان اشياء كثيرة منها انقلبت الى المقام بعد ان كانت في البسط. طيب نجري الجي. الجي ماذا يمثل؟ يمثل الكوبلين كونستانت، وهي موجودة في البسط. لكن لحسن حظنا نجد أن كل الكوبلين كونستانت هي أقل من الواحد، وكأنما هنالك واحد مقسوم على رقم في المقام، وبالتالي الكوبلين كونستانت يؤكد أيضا على سيطرة الفضاء على بعد. وهذا واضح في أن الكوبلين كونستانت نقصان الكوبلين كونستانت ينقذ الماتر انتراكشنز. يعني مثلا نعلم ان ال QED يعطينا كوبلين كونستانت 1 على 127. طيب هذا بالنسبة للترم الأول حسب البرتبيشن ثيوري. الترم الثاني يعطينا 1 على 137 تربيع. الأول 1 على 137، الثاني 1 على 137 تربيع. وهذا يؤكد على سيطرة الفضاء ثنائي الأبعاد. الفضاء ثنائي الأبعاد أهميته أو ما يفعله هو يمحي تأثير المادة مع بعضها البعض ويجعلها مثل الجزر في البحر، حيث أنها لا تستطيع أن تتفاعل مع بعضها البعض ولا تستطيع أن تؤثر على الفضاء. فبالتالي الكوبرنيك كونستانت هذا يؤكد أيضا بما أنه أقل من الواحد، إذن هو أيضا يؤكد على سيطرة الفضاء ثنائي الأبعاد، وكأنما هو عبارة عن 1 على الرقم مضروب في المقام، والرقم المضروب في المقام يزيد كل مرة ويدلل هذه الزيادة على سيطرة الفضاء ثنائي الأبعاد. إذن الفيرتكس أيضا تعبر عن سيطرة الفضاء ثنائي الأبعاد. وهنا واضح لأنه مشتقة اللاجرانج على مشتقة الفيلد الثلاث. هذه الفيلد ممكن اعتبارها مجالات خارجة من التفاعل لأنها موجودة في المقام، مجالات خارجة من التفاعل لأن هي موجودة في المقام. فبالتالي هذه المشتقة مجمل هذه المشتقة يعطينا سيطرة المقام على البسط.
That's one. Okay, questions to this rule? Yeah. Mm-hmm. What is this phi you are mentioning? Yeah. Yes. With respect to all the fields that you have in the vertex. No. You always have to take the derivative with respect to the respective fields which appear in the appropriate term. If you have a term with 4 fields, then you have to take a derivative with respect to exactly those 4 fields. Now you always take as many derivatives as you need until you get a constant. So for each field in the Lagrangian, you get a line, connecting line for each field. And then you need to take a derivative with respect to all those fields corresponding to all the lines. So if you have a vertex with 4 fields, then you take 4 derivatives, and then of course you also get a constant. And the vertex looks like this, right? So you will always get a constant. But you may be thinking also of symmetry factors, because if you have something like phi to the 4, for example, and you take the 4th derivative, you will get a symmetry factor as well, 4 factorial in this case. But that was maybe not your question, but it's... It always makes sense if you say that you always take the correct derivative with respect to the correct set of fields. So in this case, let's say the interaction Lagrangian is this times lambda. Okay. Then the rule is, first of all, the graphical rule is that at this vertex you have 4 lines, y 4 lines, because you have here 4 powers of fields, and exactly each line corresponds to 1 field, and you can literally write down a field symbol at each line corresponding to that, and then the vertex rule for this is defined by taking the 4th derivative with respect to this field. because you have 4 phi lines. So you take the fourth derivative with respect to phi. And then in this case, you will get 4 factorial times lambda, and then that would be your rule. Okay, so the rule always makes sense, but here there is an additional subtlety appearing, namely the symmetry factor 4 factorial. And we will talk about that also in a few moments. It's term by term. For each term, you get a different rule. Okay, so if the Lagrangian is that, then your list, your Feynman diagram table, looks like this. That is now your Feynman diagram table corresponding to this interaction Lagrangian. For each term in the interaction Lagrangian, you get one rule. If you have 2 terms, you get 2 rules. And for each rule, for each term, you get a rule coming from this recipe. And for each term is different. So it's the Lagrangian must be considered as a linear combination of monomials. A monomial is something which does not involve a sum, but only a product of fields and number-valued coefficients. That is a monomial. And so for each monomial, for each term in the Lagrangian, you get one rule. And sometimes this recipe here gives you a symmetry factor, and we will talk about this in a second. But before we talk about the symmetry factor, I wanted to talk about vertices with derivatives. So let's suppose you have an interaction Lagrangian that looks like this. For example, G times A mu times phi times I times d mu phi. Okay. I times d mu phi. So you have a derivative in your interaction Lagrangian. Remember, I allowed derivatives in the interactions. And so here is a simple example. Of course, this thing has a Lorentz index, and in order to make it Lorentz invariant, we can multiply it with a photon field, A mu here. Let us not worry about gauge invariance, but let's just look at this Lorentz invariant term. Okay, so what is the Feynman rule corresponding to this term? So the rule here is not sufficient, but the rule is as follows, namely, remember that we always do Fourier transformations, and I times d mu becomes the incoming momentum flowing into a field. Therefore, in Fourier space, this I times d mu becomes the incoming momentum flowing into this field operator phi here. Therefore, the rule is the following. So for this particular example, we have a rule with, so let's say phi 1 and phi 2. We have a rule with one photon field. We have a phi 1 field and a phi 2 field in the vertex. Okay? And so 3 lines connect at the dot. Now what is the value of the vertex in Fourier space? First of all, we get the I from the exponential e to the I times the Lagrangian. Then we get the G from here. And then we get the momentum from the Fourier transformation of the derivative, and this is the incoming momentum flowing into the field operator phi 2. Therefore, here in this, we have to write down what is the momentum flowing into this field phi 2. Let's call it K, or K2 to be maybe more explicit. K2, and then the rule is that K2 mu. So and the Feynman rule contains a Lorentz index, which corresponds to the Lorentz index of the photon field operator here. So that is the rule. So I times d becomes the momentum p incoming into the appropriate field operator. And so in this way, you can derive the Feynman rules also for derivatives, and then you have the full possibility to derive all Feynman rules for all cases. So this is the way how you derive from any quantum field theory the propagators and the vertices, and this is basically the.
طبعا هنا الوضع اتغير، أصبحت هناك كي في البسط، وهذا فعل ويدلل على على يعني يصب في مصلحة الكتلة ولا فضاء رباعي الأبعاد أو الكتلة والطاقة، ولا الأمر واضح بسبب أن كي داخل التفاعل اللي هي كي 2 داخل التفاعل، وهي كي عبارة عن مومنتوم رباعي الأبعاد. هذه الكي كما ذكر أنها جاية من المشتقة دي ميو، جاية من مشتقة دي ميو، فالدي ميو عبارة عن كي، لكن هناك ثلاثة فيلدز، هذه هي الفيلد يجب أن تصب في مصلحة المقام. وهذا واضح، هذا واضح من خلال ماذا؟ أولا من خلال أن فاي 1 وفاي 2 تعبران عن، أفرض أنها ديراك فيها السبينر اللي هي يو 1 ويو بار ويو. هذه السبينر كما ذكرناها في معادلة في الفيديو الخاص بنظرية تفسر معادلة ديراك. طيب تعالوا نشوف الفيديو. هذا الفيديو الخاص بالتطبيق على معادلة ديراك والحديث عن التطبيق على معادلة ديراك والحديث عن معادلة يانغ ميل. هذا الفيديو على ما أعتقد هذا الفيديو
we have not yet talked about.
لا ليس هذا. أين هو الفيديو؟ الفيديو يتحدث عن معادلة ديراك. عموما حقيقة أنا لا أعلم أين هو، لكن ستجدونه في هذه الفيديوهات، تطبيق على الجسيمات ذات اللأ. طيب عموما أيوة هذا الفيديو، هذا الفيديو عموما هذا الفيديو إثبات فرضية بخصوص اللف المغزري وحد شكل الكتل التي تخرج من التفاعل من خلال معادلة ديراك. هذه معادلة ديراك. أنا هذا الموضوع أنا كنت أريد أن أصله، أنه هذه هي معادلة ديراك. انظر في معادلة ديراك، انظر إلى المقام. هذا معادلة ديراك اللي هو السبينر يو 1 بي بالنسبة للإلكترون الداخل مثلا أو الخارج كل واحد. انظر إلى هذه المعادلة، نجد أن انظر إلى المقام. هذه المقامات مقام E زائد MC سكوير، هنا برضو تحت في MC سكوير. هذه المقام أو هذه المقامات تعطينا تؤكد على سيطرة الفضاء الثانوي الأبعاد. يعني من هنا نرى أن سيطرة الكتلة والطاقة من خلال كيميو أو الكيميو هذا K2 ميو يزيد يصب في مصلحة سيطرة الكتلة. لكن إذا عوضنا الفيلد هذه الفيلد ستصب بطريقة أكبر في مصلحة المقام يعني الفضاء الثانوي الأبعاد. وكما رأينا في السبينر هناك بسط على المقام، والمقام أكبر من البسط، لأن المقام عبارة على MC سكوير، وبالتالي نجد أن في ناهيك عن الكونتراكشن، يعني احتمال الكيميو يحصل لها كونتراكشن في مكان آخر في فايمن رولز، وهذا أنا ما أعتمد عليه. وبالتالي كلما زاد البسط صب ذلك في مصلحة الفضاء الرباعي الأبعاد أو في مصلحة الكتلة والطاقة. كلما زاد المقام كلما صب ذلك في مصلحة الفضاء الثانوي الأبعاد، وفي النهاية سينتصر الفضاء الثانوي الأبعاد، وهذا ما يظهر في كونتراكشنز الذي يحصل في الفايمن رولز. فمهما سيطر الوضع البسط، وهناك معادلات كثيرة في البسط والمقام معادلات قليلة، أعرف تماما أنك أخطأت في شيء. المفترض أن تكون معادلات كثيرة في المقام أو حدود كثيرة في المقام وحدود بسيطة في البسط، أو أن الحدود في المقام حتى لو كانت بسيطة من المفترض عندما تحاول فيها بطريقة حسابية تكافئ وتزيد على البسط. هذا ما أريد أن أقوله.
All the rest is the same as in QED, and so I will now make a list with some statements which are kind of maybe a little bit boring, but I want to write it down in a coherent way such that we get a full list of Feynman rules, what you need to do if you want to evaluate in any theory, any Feynman diagram. Let's collect it here. But the rest is now not surprising anymore. So first of all, in a Feynman diagram for the S matrix, we also have external lines, and they are the same as in QED. External lines, they are as in QED. So for vector fields, you get those polarization vectors, epsilon mu. For fermions with spin 1/2, you get the U bar, V bar spinors in the same way as you do for QED. The only thing that we did not yet discuss are scalar fields. But the corresponding thing to the U and epsilon for scalars is just the number 1. There is no such vectors in the case of scalar fields. Vector 1 in the field operator, where you have the U for the fermion field, you have simply nothing in the case of a scalar field. So that is simple. And then for the S matrix, we have the following rule. S Fi for a process initial state going to final state, we write it as Kronecker delta Fi plus I times momentum conserving delta function, sum of the incoming momenta minus sum of the outgoing momenta, times Tfi, and the Tfi is the interesting object, and this I times Tfi, this is the sum of all Feynman diagrams. So, and now let me write down a list of rules how you get all the Feynman diagrams. All the Feynman diagrams are obtained by combining the Feynman rules that we have listed on the 2 blackboards in the following kind of obvious way, but as I said, let me just write it down in a coherent way. So the incoming or outgoing lines They correspond, of course, to the particles in your process. You have as many incoming and outgoing lines as you have particles in your process. So we can say they correspond to the states I and F, to the initial state and the final state of your process. Then the rules for the propagators, which are the internal lines and vertices, they are as above. So these are the sets of rules that apply to the vertices and propagator. And then the Feynman diagrams are, of course, obtained by connecting all the vertices and all external lines in all possible ways. Connect the external lines with vertices in all possible ways. And each diagram then corresponds to a certain contraction. And just to remind you, the contractions are obtained in this schematic way. You take the final state and the initial state, and in between you have the time-ordered exponential function of I times the integral over the interaction Lagrangian density. Okay? And so you replace final and initial states by creation and annihilation operators, and then you have an expression that you can evaluate step by step in perturbation theory using contractions, and there is this correspondence between the diagrams and this here. And if you are in doubt what the correct Feynman diagrams are, it's always correct to go back to this expression and to evaluate symmetry factors, minus signs or whatever. Or to check whether you have forgotten diagrams or something like this. Then the symmetry factors. So the 1 over n factorial from the exponential, and also factors from these derivatives that we have mentioned, the L int derivative with respect to phi. There can be symmetry factors as well, like this 4 factorial in the example. They typically cancel. But not always. And therefore one has to do a case-by-case analysis of those symmetry factors. But for example, in QED, it is rather rare that you get non-trivial symmetry factors and that you need to take into account anything. But in other theories, it happens more frequently. In particular, in such a theory where you have such a field and such a vertex, phi to the 4, where you get this 4 factorial, there you often encounter such symmetry factors and not completely cancelled 4 factorial factors and so on. So, but this is just a general statement here. Then there are the minus signs, relative -1 possible in case of fermions. And at each vertex we have 4 momentum conservation. And for loop diagrams, the integral over this undefined loop momentum remains.
Right.
So this ends the main set of rules, and what is left is only one remark, but we've
طبعا هنا ذكر أن في اللوب دياجرامز في مومنتوم يمكث. ما الذي يجعل المومنتوم يمكث في اللوب دياجرامز؟ لأنه اللوب يكون الصراع فيها قوي، يعني اللوب يكون الصراع فيها قوي جدا جدا، ولكن الغلبة ستكون للفضاء على بعض غير متناظر، وبالتالي هذه المومنتوم الذي يمكث سيذهب بطريقة أو بأخرى، سيذهب لا محالة له إذا كان موجود في البسط وليس المقام، وإلا سيكون هناك مشكلة كبيرة جدا، فيجب أن يذهب، أو سنجد ما يعادله في المقام. سنجد ما يعادله في المقام. أما إذا كان هذا المومنتوم في المقام، هذا يعني عبارة عن طاقة مطرودة أو كمية تحرك مطرودة من التفاعل، فلا بأس في ذلك، مع الحفاظ على momentum conservation.
Before I do the remark, let me give you again the chance to ask questions. This would be the complete list of rules for general Feynman diagrams for any theory for the S matrix, and remember in the videos you can also see Feynman diagrams for green functions, which are similar but not exactly identical. So if there are no questions, then let me do the remark, which is technical. Namely, the point is that the rules here are correct, but the derivation is not in all cases as simple as in the case of our example for QED. In some cases, in some theories, obtaining those simple rules involves certain tricks. And let me write this down. The rules for derivative interactions and vector field propagators. They do not directly follow from our procedure. The rules for derivative interactions and vector field propagators. They do not directly follow from our procedure. But there is a cancellation. So we have actually several issues at several places. There are some problems with our procedure. Namely, let me maybe, since we have 10 minutes of time, let me indicate the problems. Problem 1 is the Hamiltonian density is not always equal to minus the interaction Lagrangian density. That is not always true. But we have assumed this to be true in our derivation, because initially our derivation led to an exponential function here for time-dependent perturbation theory, where in the exponent, of course, there is the Hamiltonian, because the Hamiltonian generates time evolution. But then we simply said, okay, normally this is true, and we replaced the Hamiltonian by the Lagrangian density. Good. But it's not always true. For example, it is not true if the interactions involve time derivatives, and it is also not always true if you have vector fields. It's actually true for the photon, but for example for the W boson or for simplified massive vector fields, it might not be true, this statement here. And then we have a problem at this point. And then the point is that the Lagrangian is Lorentz invariant, whereas the Hamiltonian is not Lorentz invariant. So we have something non-Lorentz invariant replaced by something which is Lorentz invariant. So that is the first problem. The second problem is that, for example, here, in the derivation from our procedure, we would of course get this here, or we would also get this sort of thing. Okay. This is a contraction. If we have derivative interactions, it will happen that we get a derivative of a field in a time-ordered expectation value. And then in the formalism that we are using, this is not automatically equal to, let's say, the outer derivative of this expectation value. Okay, so this is not necessarily equal. And the difference between those two expressions is that this is, of course, Lorentz invariant, because the expectation value is Lorentz invariant, and its derivative is, of course, also Lorentz covariant. But this is not, because of the time ordering of time derivatives. It's not Lorentz invariant. So we have a non-Lorentz invariant expression here. And also in the case of massive fields, this is not Lorentz invariant or covariant. If you have a massive vector field and you quantize it in the way we did in our chapter 2 of the lecture, then this expression can be evaluated from everything that we have discussed, and the result is just not Lorentz invariant or covariant. Okay, so this is also a problem. And however, the point is, all these problems cancel. So that means if you ignore everything simultaneously, then the procedure is correct. That means the non-Lorentz invariant term here in this transition cancels exactly the non-Lorentz invariant terms appearing in those time-ordered expectation values. And therefore, if you ignore everything, then it's correct. Okay, and the third problem, let me add this. This propagator is not the inverse of the corresponding differential operator. Because that would be Lorentz invariant. So the differential operator is, of course, Lorentz covariant, and so its inverse is also covariant. But this is not covariant, and therefore it's not the same. And so if you ignore all these difficulties, then they cancel among each other, and the rules that I've already stated are completely correct. The only question is what is the best way to derive the correct rules also in those cases. Now we have basically obtained them from analogy to QED. In QED, those problems don't exist. And I simply claim that those rules are always true. And I want to make you aware of the subtleties here. And so in that sense, it's an advertisement for the Quantum Field Theory 2 lecture, where one can do the path integral derivation of Feynman rules, which is a derivation which manifestly, directly, automatically leads to those rules and which avoids all these problems. And therefore, this is also a proof that indeed all these problems cancel. But if you want to do this in the context of this operator canonical quantization, then you really need to sit down and figure out all those non-Lorentz invariant terms and check that they indeed cancel out. And the fact that they cancel is, of course, a reflection of the fact that the underlying theory is indeed Lorentz invariant. It's Lorentz invariant by construction because it comes from a Lorentz invariant Lagrangian, which is quantized. Therefore, there is no reason at all for the final theory to be not Lorentz invariant. It is Lorentz invariant, and therefore those subtleties, they are a reflection of the fact that the Hamiltonian formalism singles out time and therefore breaks Lorentz invariant or doesn't treat Lorentz invariance in a manifest way, and therefore you get some subtleties which in the end cancel out. So it's a drawback of using the Hamiltonian formalism. And the path integral is a formalism which is built to manifestly preserve Lorentz covariance, and therefore in this approach all these problems do not appear. Okay, but the statement remains that those set of rules here are correct in even those cases. And just to reiterate, for QED, these subtleties are not existing. For QED, our derivation completely directly leads to the correct rules without any detour. All right, I think then we can stop, and tomorrow we will go on with a new chapter. So we have now enabled ourselves to calculate Feynman diagrams and therefore calculate processes. And so now we will look at QED more seriously, also from the physics point of view, and we will calculate Feynman diagrams, but not only to understand Feynman rules, but to really study the quantum field theory and predictions of QED and what is the impact of the quantization of the photon field and the electron field. And depending on how we proceed, we might also come to the context of one loop calculations in QED in this semester, so that you also see this rising of higher order effects which give rise to interesting new phenomena. Okay, so this is the plan which we will begin with tomorrow. See you then.
إذن يوم غد إن شاء الله ما سنفعله هو سنركز مع الدراسة سنركز على أنه كيف هذه الكونتراكشنز تعمل على زيادة المقام على زيادة البسط. يعني ذكرنا أن نحن الآن ذكر المحاضر أن هناك مشاكل، لكن هذه المشاكل تحل آنيا أوتوماتيك بطريقة هي تحل نفسها لوحدها، وهذا يعني أنه الفضاء الصناعي بعد وجد طريقة لحل هذه المشاكل، وبالتالي جعل المقام أكبر من البسط. في الحلقة القادمة سندرس هذا جيدا بإذن الله تعالى، وسنرى إذا كانت فرضية صحيحة أم لا. والسلام عليكم ورحمة الله.